as the linear transformation. In terms of the matrix method, we can do express. So that is called as the DFT as a linear transformation. We'll see that one. So what we'll do is we are going to express the DFT formula in terms of the linear transformation. We are going to express in terms of the matrix method. We are going to express, and we'll find the expression for that one. So for that one, what shall we do? So we are going to consider the DFT formula. We'll consider. So let us consider the DFT formula, that is x of k is equal to summation n is equal to 0 to the n minus 1 x of n into omega n to the power of kn will consider. So here k can take the value 0 is less than k is less than or equal to the n minus 1 will take. So in order to express as a linear transform set of linear equations, we are going to expand this one horizontally by substituting n is equal to the 0 to the n minus 1, and similarly we are going to expand vertically by substituting 0 to the n minus 1. So if we expand horizontally, it will become x of k. So this is equal to the, so if I substitute n is equal to 0, it has become x of 0 into omega n to the power of 0 plus x of 1 into omega into the power of k plus x of 2 into omega n to the power of 2k, and so on. It will become x of, if I substitute n is equal to n minus 1, the final limit, it is small x of n minus 1 into omega into the power of k into n minus 1 will get. So call this as equation number 1. Call this as equation number 1. So what we'll do is this equation we got. Now let us substitute k is equal to 0, 1, 2, 3, and let us expand vertically. So this has become k is equal to 0. If I substitute, it has become x of 0 is equal to, so it has become x of 0 plus x of 1 plus x of 2 and so on up to the x of n minus 1. So call this as equation number 1.1. And similarly, if I substitute k is equal to 1, so if you substitute k is equal to 1, so this has become equal to the wherever the k is there, we can substitute that as k is equal to 1, and we can find out the expansion. So it will become x of 1 is equal to x of 0. So wherever k is there, we'll substitute as 1. So x of 1 into omega n to the power of 1 and plus x of 2 into omega n to the power of 2 and so on up to the x of n minus 1 into omega n to the power of k value is 1. So it has become n minus 1. So call this as equation number as 1.2. So similarly, let us substitute k is equal to 2 and so on up to the k is equal to the n minus 1. So we'll get x of n minus 1 is equal to the x of 0. Wherever k is there, I'm going to substitute as n minus 1. So x of 1 into omega into the power of n minus 1 plus x of 2 into omega into the power of 2 into n minus 1 plus so on x of n minus 1 into omega into the power of n minus 1 the whole square. Call this as the equation number as 1.n here. So we are going to combine the equation 1, 2, that is equation 1.1, 1.2, again 1.3. So in order to express as a matrix here, so we can express the terms x of 0, x of 1 up to the x of n minus 10 as a column matrix, and these terms we can express as the square matrix, and x of 0, x of 1, 2, it's a common for all the equations, we can express as a another column matrix. So we are going to express the above equation in terms of the matrix method. So we'll express the above equations, expressing the above equations. So in the matrix method, in the form of matrix method, so what we'll get is, so we'll get one square matrix, column matrix will get here x of 0, x of 1 up to the x of n minus 1. So this has become one column matrix. On the other end, it has become, so all the terms are 1, 1, 1. So next is 1 omega into the power of 1, omega into the power of 2 up to the omega into the power of n minus 1, and similarly we'll get 1 omega into the power of n minus 1 omega into the power of 2 into n minus 1 and so on up to the omega into the power of n minus 1 the whole square. So this is the one column matrix we got here, and we have the other column matrix we'll get. So the another column matrix, which will be the matrix of x of 0, x of 1 and so on up to the x of n minus 1. So this equation, it's a matrix of the order n cross 1, and this is the matrix of the order n cross n, and this is the matrix of the order n cross this is of n cross n, so that when you're going to take the matrix multiplication, the resultant order will be equal to the n cross 1 matrix you'll get here. So this equation will express the DFT as a linear transformation, so that we express the set of, in the terms of the set of linear equations we expressed here, and we got this as the matrix method of finding the DFT of the given sequences we got here. So in general, we can express this as so x is equal to the omega n into small x here. So this will express the DFT as a linear transformation here. So this expression will express the DFT as a linear transformation. So linear transformation means we converted a set of linear equations, and we converted in terms of the linear transformation, and we got it expressed in terms of the matrix method we expressed here. So this is how we can find the DFT of the sequence by using the matrix method. So the advantage of finding the matrix method, using the matrix method in finding the DFT, is that so we can reduce do calculation of the small endpoint DFTs in the simplest way we can do calculate, and it is easy to find the values easily. For example, if I take n is equal to 4, for n is equal to 4, I'm going to write the matrix method here. So n is equal to 4 means x of 0, x of 1, x of 2 and x of 3. So here we can use the matrix method. So here this is the twiddle factor matrix will become like this. So it's all terms are 1. So this is 1, omega 4 to the power of 1 and omega 4 to the power of 2 and omega 4 to the power of 3. So next is omega 4 to the power of 2, omega 4 to the power of 4 and omega 4 to the power of 6. And next one is omega 4 to the power of 3, omega 4 to the power of 6 and omega 4 to the power of 9, omega 4 to the power of 9. So this has become the matrix. So the matrix is the input matrix here. So these terms are x of 0, x of 1, x of 2 and x of 3. This is the matrix of order 4 cross 1 we'll get here. So now we know the values for the twiddle factor. Let us substitute here, and we can use this as the general method for finding the DFT. So this has become x of 0, x of 1, x of 2 and x of 3 here. And by substituting the values for the twiddle factor, we get, so this is 1, 1. This is omega 4 to the power of 1, 2, 3. And we know the values for this one. So it's a 1, 1, 1, 1. And the next terms are 1 minus j, minus 1 and plus j. And this is omega 4 to the power of 2, which is nothing but it's a minus 1. Omega 4 to the power of 4 is 1 and minus 1. And this is 1 plus j. And omega 4 to the power 6 is minus 1. And this is minus j. And we got these terms are x of 0. This is x of 0, x of 1, x of 2, and x of 3. So this is how we can express the DFT. This is how we can express the DFT as a linear transformation, so that we can kind of use this one to find the DFT space by using the matrix method. So similarly with the IDFT matrix method like this. So the DFT for finding the IDFT of the given sequence. So what we can do is we can express, so this equation is there. this equation, for that one we can multiply omega n inverse on both the sides here. So it will be expressed as the finding the IDFT. So we can call this as a matrix method to find the IDFT. Find IDFT is that. So by considering that one, x is equal to omega n into small x. So we are going to multiply both the sides with the inverse of the matrix omega n inverse. And if you are going to solve here, and we can able to obtain the inverse of the matrix will become equal to the x. So it is equal to the 1 by n into, so omega n inverse into the capital X will get. So this is nothing but omega n to the power of, and also we know that omega n inverse is nothing but it's a omega n to the power of minus n here. So minus n into x will get here. So like this we can use this method to find the inverse DFT by using the matrix method. So these two above equations will express the DFT as a linear transformation, so that we can find out the IDFT by using the matrix method, and DFT also we can find out by using the matrix method. The next question,